Learning, Dr. Raia Hadsell. Raia is a research scientist and director of robotics at DeepMind. So as a full disclosure, we are normally sitting not far from each other in the London DeepMind office, but for the past 4 months, we have been working from home. Raia's scholarship and research interests span from embodied robotics to deep reinforcement learning agents, with an emphasis on navigation, lifelong continual transfer learning, and on addressing fundamental challenges in robotics. Raia's PhD thesis with Professor Yann Lequin at NYU focused on machine learning using Siamese neural networks, also known as the triplet loss, and on deep learning for mobile robots in the wild, with a dissertation on learning long-range vision for off-road robots, which won an outstanding dissertation award in 2009. Raia's unique professional journey started with an undergraduate degree in religion and philosophy from Reed College in Portland, Oregon, and involved a postdoc at the CMU Robotics Institute in Pittsburgh, Pennsylvania, with Professor Drew Bagnell and Marshall Hebert, as well as technical management at SRI International in the Vision and Robotics Research Lab in Princeton, New Jersey. Finally, Raia is also the program co-chair for the NURBS 2020 conference, which will be fully virtual this year, and which innovates with a broader impact statement requirement for all the submissions. So let us now welcome Raia.
Thank you very much, Piotr. Thank you very much. Happy to be here. And thanks for agreeing to question me, and looking forward to the conversation.
This is fantastic. So we have, I'm certain, a large audience. We are going to use our imagination that they are listening, and it's really exciting. So, wow, maybe we can start with some questions about your day-to-day research as a scientist. So you're a research scientist at DeepMind, and you're director of robotics. You have been working in research at DeepMind for the past 6 years. Prior to that, you worked as a postdoc at CMU, as a research scientist at SRI. You did a PhD at NYU, so you have an extensive experience of conducting research, and also a very diverse career. So given your very inspiring achievements and expertise in that field, is there something that you could share with the attendees of the conference? There was a question on Slido that focused actually on the process of day-to-day scientist life. And let's leave for the side, on the side, any management duties. Let's just focus on the research component. So the question was, how do you divide your time? What major activities could you identify? How do you divide maybe implicitly your time between all those activities, reading papers, coming up with ideas, talking ideas through with colleagues, conducting and running experiments, coding, writing drafts, full papers, etc.?
Thank you for the question. So a good amount of my time these days is taken up by management duties. I will indeed put that to the side and focus on the rest. I think that it's all about these days having a balance between thinking about quite long-range research efforts and then thinking about more immediate efforts. So I feel like as the leader of a research group and the robotics lab, I really need to spend a good amount of time each week thinking about and planning for what we're going to be doing in a year or two. So what are the right challenges for us to take on? How should we plan our activities? What are sort of the new directions that the field is in? So sort of that longer term strategic research thinking is definitely a good chunk of my sort of research work. And then the other component of it is the more immediate thing. So talking with people, looking at their results, their experimental results, or talking through their technical issues, and then pulling together the fruits of that process into papers, either journal papers or conference papers. So that's really at the heart of it. I try I try hard to keep also abreast of where the field is at in terms of reading papers and looking at what other people are, what other labs are working on. I think that it's all important. There's so much going on at DeepMind. I think there's a challenge for all of us to make sure that we're also looking outside of DeepMind at what's going on elsewhere, but definitely trying to do that. And then the last piece of my work is with NeurIPS and other conference organizations. I also help with the organization every year of iClear and also Coral, as well as NeurIPS this year. So time there.
So as a researcher, how many new research papers would you read every week?
Not as many as I would like to. I'd say that I give a quick read to everything that gets sent to me, but that may only be a 10-minute run through of the paper. It varies a lot. Some weeks it'll be 2 papers and some weeks it'll be 10 papers, but those are probably the bounds.
Mm-hmm. And when you were a PhD student,
then did I read more papers then?
Yes.
It would depend. It goes in waves. Sometimes I tell the people that I work with to stop reading papers because it can be a little bit discouraging to see all the other things out there. Instead, you need to really focus on what you're doing and ignore the rest of the world sometimes. So it goes back and forth. And then sometimes you want to only look at what else is happening. Mm-hmm. I've realized since going to this work from home mode that I used to read a lot of papers on my commute to and from work. I don't have that anymore, so mm-hmm. Perhaps I need to build the equivalent into my day.
Hmm. So is there something about context switching for being in paper reading mode because you're doing literature review or before writing a paper because you need to figure out if anybody has scooped you, and the coding mode, and so it can be at the level of a day or even a week?
I tend to break things up more on the level of maybe a couple of hours, so multiple different context switches during the day. But to each their own.
There was a question about coming up with ideas for new research papers.
Well, there are different types of research ideas. There are ideas that go way back, so something that you asked or had a real an insight about, and that might have happened a couple of years ago, and that same thought comes back to you and nags at you, and eventually you say, okay, let's try this out. And you find the right people that want to work on this with you, and you try something out. Other things come from elsewhere. Other people's ideas get proposed, and I say, that sounds like a great idea. It's a real variety of things. I think the longer that I am in this career, in this research world, the more I realize that the same ideas are really there. They sort of tug you along, and it's sort of these paradigms of things that you think need to work or that should work, or outstanding problems. You keep on coming back to those because you feel like there's got to be a better solution here. So those often drive me, and I'm not sure if that's just me or if most people end up with these sort of lifelong ideas that pull them along.
Thank you. There is another question that this time pertains, I guess, to a difficult part of research, and so it will be a moment of honesty, I guess, in the answer. What do you do when you come up with an idea, implement it, and then realize that the results are not so good? Do you still go to publishing the paper, or do you move on?
I would have to say neither of those. So it's often hard to, I believe that it is good to publish negative results. But usually when we get negative results, we have the feeling of, but that can't be right. There must be a way that this can work, because often those ideas, like I said, come from these sort of long-held, intuitions or insights that you feel this must have a way that it works. So if it doesn't work one time, then we don't just publish it, say, oh well, it's a bad idea, and move on. Instead, we just keep on working with it, right? So maybe we take a break, maybe we change it, we come back to it, but it's a process, right? It's not a single thing. So I'd say neither. It's hard to just publish bad results, because then you're also saying that this is a failed idea, and that you're going to move on. Mm-hmm. But usually we don't do that. We find a way to make it work.
Yeah, that's a great lesson, because it's about perseverance and failing in experimentation, but doing so in a slightly more structured way. You're not just randomly trying ideas. You're
right.
Yes, you're methodical. Okay, so a little bit going back in time. Let's start with a triplet loss. So towards the earlier part of a PhD at NYU, what you did at with Professor Jan Lequin at NYU, you published, along with Jan and with Samit Chopra, 2 seminal papers on the so-called triplet loss: learning a similarity metric discriminatively with application to face verification at CVPR 2005, and dimensionality reduction by learning invariant mapping at CVPR 2006. And these 2 papers established that technique in computer vision. So one of the questions from Slido was, what is your opinion on learning that similarity metric discriminatively today, with regards to all the current work on generative adversarial networks? Could it be used to train more modern architectures like GANs and even tasks?
Yeah, I saw this question. I think that it's a really interesting question. Using a triplet loss, or learning using pairwise constraints, it's a discriminative learning approach that tries to learn a relationship between data, between samples, that reflect some of the underlying maybe semantics that are there, and compared to simply class-wise labeling, training a one-shot discriminative classifier, for instance, then there can be a lot more information there that's used to build this manifold, or this similarity metric between different things. But it is still a lossy process, because you can say, let me learn a similarity metric between all of these different images of, I don't know, fruits. And what the neural network might end up doing is simply relating the color of the fruit. So it might end up sort of clustering things by color and throwing away all of the other important information there, because it's not important to solve that problem of getting the right pairwise distance between things. So this type of approach works really well, for instance, for faces, where there's a lot of subtle information in there that goes into discriminating, 2 faces that are from the same person versus two face images that are from different people. But for some things, it can be quite lossy. Generative models, on the other hand, are going to try to preserve a lot more of the information of the data that's there, and not be so lossy. On the other hand, they're going to focus on elements like particularities of the pixels and the texture and things like that might not be important for the semantics. So, long way to say this, but I really like the idea of bringing together a triplet loss and learning from this pairwise constraints, and a generative method that tries to preserve all of the information. There have been a couple of papers that have gone in this direction of marrying together for instance, an autoencoder with a pairwise constraint, with a triplet loss. So a couple of works were done by this in Jan LeCun's lab. But I think that doing this with GANs might work even better in terms of using a pairwise discriminator within the GAN, and that would make a lot of sense. So yeah, I haven't seen this being done yet, but I think that it's a good direction.
Well, thank you for the great research suggestion. So now moving forward in time and moving towards the field of robotics. So you're the director of robotics at DeepMind, and there was a pretty strong question from on Slido. Why is robotics behind the rest of the AI and machine learning community? The latter often solves the problems in simulation, and it's rarely shown to actually work on physical systems, whereas robotics needs to work on physical systems by definition. So is working on systems something that is left to engineers rather than to researchers? And there was a different way of phrasing this question, which could be, do you think the research cycle when doing robotics and machine learning is orders of magnitude slower than the rest of machine learning?
Yeah, I have heard somebody else, I think it was Alyosha Efros, he said that robotics is 10 years behind computer vision. And I think that that is absolutely true. And hopefully it's not a gap that's widening, but one that is closing. But I do think that where other fields, speech, language, vision, have all really profited from compute that we have, massive distributed compute, and also data sets. And so that's made it possible to apply lots of large-scale deep learning methods that train end-to-end and work really well. The problem with robotics is that it's about taking actions. Those actions then change the environment that you're in. They change the robot. And so you cannot learn from distributed compute and a static data set. Really, the problem is learning through interaction, which is also the problem of reinforcement learning. But with robotics, then you also have this, you also have the hardware, you also have the actual robot. And so while we can simulate robots, and certainly a lot of work is done on that, then there are real problems with doing research on the actual hardware, on the actual systems, that only makes it more challenging to apply deep learning and deep reinforcement learning approaches. You know, in particular, it's hard to, there are not a lot of platforms that are built for learning from data. Learning from data on a robot implies that you're going to use live sensors, and you're going to actually take actions in the world, and that you're going to interact with the world. And most robots that are out there, they're not robust for this. They're not sensorized in the right way, and they're just not able to gather that amount of data. Plus, the compute is necessarily there, sort of close to the robot, and that makes it hard to take advantage of much larger cloud computing solutions. So there are a lot of challenges there. There are there's headway being made. I think that we are making a lot of improvements in what we can do with robotics and learning methods. But I think there's always going to be some challenges there until perhaps we have different types of robots entirely. But then there's a chicken and egg problem with, proving to robotics companies that they should make robots in a different ways, where maybe they trade off from the precision of a modern industrial robot. Maybe they lose some of that precision, but then they gain some robustness in terms of interaction and colliding into things and things like this. Mm-hmm. So yes, robotics is behind, but I believe that it is catching up. And I am looking forward to being really on the other side of this revolution in another 5 to 10 years.
So you mentioned essentially data scarcity, and you evoked the idea of asking robot companies to generate different kinds of robots. Do you think of $10, €10 robots, or maybe 50, €100 robots that are easily breakable and can be run in high quantities?
I don't want to break robots. That's the point. So I think that, like I said, there's a trade-off there. I don't know that robots are necessarily going to get much cheaper, but if we want to deploy 1,000 of them to learn how to move in a different environment, or how to interact with each other, for instance, then obviously cost is a factor, but robustness and sensorization is also a problem. So ideally, we would have robots with different types of capabilities, move beyond the 2-finger pincher grasp that most robot manipulators use, to the sorts of things that we can do with a full hand, to move away from wheels and towards legs, which is a more general, more agile way of locomotion. So having robots that have these capabilities and that are not easy to break, and that have enough sensors that we can tell when we bump into each other, that we can feel when we pick something up. I think these are all the critical things. It's not necessarily going to come with a €10 robot or €100 robot, but there has to be some trade-offs and some middle grounds there, and we need to convince robotics companies that there is that we can get to much better control, much better perception if we have these robots.
Okay, thank you. So you evoked the issue of noise, and there were 2 questions which are related to specifically on that problem, asking for answers. How do you train agents to handle high environmental noise, which is not easy to model in simulation, but appears in the real world? And how to handle the delay in the perception? Do you have some recipes now?
Well, so domain randomization has been used a lot and quite successfully. However, it comes with a price. I mean, this is an approach that's been used in sort of computer vision and probably other domains for a long time. Let's just augment our data set to add some noise, skew things, change colors, etc. We're not changing the content of the data. We're changing the properties that are not critical to the task. And this works up to a point. So you can train a reinforcement learning agent with this domain randomization to subtly change the task, and they can learn to be more robust. On the other hand, you're also making the problem more challenging by adding all of these factors of variation. I think that probably a better solution is something that can handle fast and slow learning, so that you can manage to adapt very quickly, so that when the robot is moving along and then the sun comes out and all of a sudden there's hard shadows and bright lights and specularities and reflections and such, that instead there is a very fast adaptation that happens. So it's not that you've learned across every possible different lighting condition. It's simply that you can quickly adapt and become robust to that. So I tend to prefer those type of solutions. Probably the 2 go hand in hand. You both learn over those different types of variations, and you also respond quickly and adapt quickly online to changes. With regard to now delays, that's an interesting question as well, something that we often ignore because we have perfect compute, or we're working in simulation and there is no delay whatsoever, there's no latency whatsoever, and people are surprised when you add a little bit of real world delay, add a little bit of real world latency, and the learning algorithm completely falls apart. It's not what we want. I think that an easy way there are easy ways and there are more challenging ways to solve this. So one is to increase the observation of the robot so that it's seeing more data at a time. You can do this by adding a recurrent network to the robot so that it's able to accumulate more state information together. So this is also a solution for POM-DPs where we only have partial observations, but this works as well for perception or action latency. So that would be sort of the easy solution. Add an LSTM, or at least stack your observations over time. A harder but more interesting approach would be something like hierarchical RL, where you are making decisions about trajectories to take rather than individual actions. So you're relying less on an action observation tight loop. And instead you're thinking more about broadly, what is the whole trajectory of my action going to be? And that is the type of control you're using. So two different types of approaches there. I think it's a really interesting question and probably an under-researched one.
Mm-hmm. Okay. Well, thank you. You mentioned the issue of adaptation to changes in the environment, and so I guess that falls under the broad category of generalization. There was specifically a question on that. What is the strategy to learn an agent to be adaptive to unseen environments, especially if they have continuous control, not discrete control? And I guess there was another question that is related. Can we make learning in situ, which I guess I understand learning at deployment, possible?
Right. So this allows me to put on my other hat, which is the continual learning, which is an important problem for robots because we can't always predict what the conditions that they're going to be in. And like I said, rather than assuming that we can train over all possible conditions, instead, let's think about how a robot or an agent can adapt quickly over time. But that brings us to the problem of sort of continual learning, of being able to adapt on deployment to new environmental conditions, perhaps changes in the robot where it might, the classic example is the leg breaking scenario. I've broken a leg. How do I still keep on moving along? Or new tasks that we want to solve, right? So we can have changes due to environment conditions, the robot itself, or different tasks that we want to perform. And the challenge is of being able to learn something new without forgetting old things and being able to do this quickly. There are a few different solutions that are out there, and this is luckily, I think, a really active area of research right now. So there's a lot of new papers coming out in this area and a lot of interest. There's a few different families of methods for continual learning that are applicable to reinforcement learning and continuous control. One is based on architectural changes. So being able to make a more modular architecture or a hierarchical architecture can help you to learn quickly or generalize well. Another family of approaches relies on the actual optimization. So how do we manage the gradients of our gradient-based optimization such that we don't wipe out what has been learned previously? So there's a lot of methods in this category. And then a third area might be memory-based methods, where we're going to use some method of memory in order to encapsulate what we have learned before, what we have seen before, and be able to quickly recall that, recall that information. So let's imagine all the different ways in which we can break the legs or change the robot in different ways, change the friction, change whatever, learn from that, and then be able to have that in memory to bring it back. Of course, memory architectures are themselves difficult to train, challenging to build, so they come with their own set of problems. But those are some of the different areas. I think, honestly, that they all have a lot of promise to them. I'm not going to cast my vote for any one of those three areas.
Okay, thank you. There was still another question that I think was digging deeper in that whole idea of on-policy learning. Someone was asking if we can reuse gathered data sets with off-policy algorithms rather than use on-policy algorithms for robots.
Yeah, it's true that because of data efficiency, off-policy learning algorithms are much more, make a lot more sense for robotics. If we have off-policy learning, we can gather quite large data sets. We can have more stable performance over time, as well as more data efficiency over time. There are challenges to that as well in terms of being able to change quickly. You sort of want to have both stability over time, but also have a sort of be able to quickly change, and that implies more on-policy learning. I think that for the most part, the research that we do at DeepMind in robotics is all based on off-policy methods.
Okay. That kind of settles the question. So now I took the liberty, in addition to looking at the questions from Slido, to also add questions that researchers in your own team at DeepMind, in the lifelong and embodied deep learning team, have been asking recently. And they pertain to two different aspects. One is rewards for robotics. So is reinforcement learning useful at all for learning interesting behaviors? Because we often don't know how to accurately specify interesting behaviors with rewards. What is your take on that?
Well, if you can specify it with a reward, then it's not an interesting behavior, is it?
Great.
Interesting behaviors are to some extent the things that we don't expect or we can't program. I think that there's a lot of different ways to use rewards in reinforcement learning. So you can use rewards and shape them and have incremental rewards and really try to scaffold exactly the type of solution that you want the agent to find. Or you can put a sparse reward on the outcome, on what you want the agent to achieve, and then the how of the behavior that solves it and gets to that reward is really something that's a bit of a mystery, right? And that's what a lot of the fun is of reinforcement learning, is placing that sparse reward, say, on winning a game of chess. And the question is how? How is the agent going to find a good solution, and is it going to be something that was different than what we predicted, as is often the case. So that is, I'd say, the thing that makes those of us that work on reinforcement learning keep coming back again, because we're interested to see what behaviors are found for the really challenging scenarios. So yes, I think that that RL is very useful for learning interesting behaviors. It's challenging, of course, as well. There's lots of cases in which we fail to ever find a solution for that sparse reward.
Yeah. And actually, there is even a whole department at DeepMind on everything that could possibly go wrong with reinforcement learning, and it often generates interesting videos. Yeah. So let's not get even a little bit more spicy. and talk about the deep learning orthodoxy. I mean, actually break it. So the question from members of your own lab was about priors. Humans are born with built-in priors, reflexes, that they acquired through evolution, not just during their own lifetime. So is it reasonable to hard code those priors in the agents?
So this does come up. This does come up often. In particular, for robotics, then there are two human reflexes that are relevant. One is the grasp reflex, so you touch the palm or the foot palm of a baby, and they will automatically curl their fingers or curl their toes around that. So that's the palmar grasp reflex. And then there's also a walking reflex. I don't remember the name of this. They have particular names, but if you hold a baby upright, one that can't even crawl yet, let alone walk, but touch their feet lightly to the floor, then they will start to sort of paddle along, and they will have that reflex. So these are obviously really useful reflexes to have. And so, of course, it seems like a reasonable and acceptable thing to build those into an agent. I'd say that my problem with that is not that it breaks deep learning orthodoxy, but more that, well, maybe it is that it breaks deep learning orthodoxy. The question is, what would that agent discover without the reflexes? So when you put in those reflexes, you are building in part of the solution. That was a good solution for humans who have evolved for millennia. But the question is, what is the right solution for a robot? That's not a human. It's nothing like a human. So the robot, whatever sort of quadruped or, just a manipulator arm or whatever it is, there are, maybe there is a different type of reflex that is the one that is valuable for it to learn. And I would rather see that happen from data and from the architecture that we use than to code it in there. So that's one reason. It's, again, going back to, can we learn interesting behaviors? Yes, and we don't know what they are. So let's just use data and learning and see what comes out. See what reflexes are learned by that agent because of data. There's another reason, though, to go with learning rather than hard coding in a reflex behavior. So when I touch my palm, I don't feel any inclination to curl my fingers around. Why? Because that was a reflex that I had when I was a baby. And you grow out of all of those reflexes. They no longer control your behavior. And it's not a switch that just turns off that says, oh, okay, now the baby is 1 year old, it's going to stop doing this. It happens gradually because you learn to override it in particular situations. I think it's hard to combine an end-to-end learning system with something that you've hard-coded in. How do you negotiate between when should I use the reflex and when should I decide not to use the reflex? So it can make your life actually harder to build in any of the components of the behavior. Then you need to learn how to use or not use those different behaviors, those different reflexes. So I generally will argue against building in reflexes. Sometimes we're just making an application. We really want to have we want to make the exploration easy. It might make sense to do it, but it's not sort of the final answer. I think that should come from learning from data.
Well, thank you. That was an interesting take on the anthropomorphization of our view on robotics, or we think that everything has to map to how we have evolved and been learning. Okay, so let's switch topic now to continual learning. And we're going to expand beyond embodied robotics and consider the general problem of learning across across the lifetime of an agent. That could relate to your work on overcoming catastrophic forgetting in neural networks that you published at PNAS 2017, Proceedings of the National Academy of Sciences, or progressive neural networks, policy distillation, or distro, robust multitask reinforcement learning. So there were several questions on Slido that pertain to that field. The first one is, could you point out the right research direction of how ORL agents can learn continually? If the agent is deployed, how can you still keep improving it?
Right. So I guess I jumped the gun a little bit earlier, and I mentioned some of these different sorts of solution areas, but let me mention them again. And like I said, I'm not going to pick a winner from between these. I think that they all have value and that they can be used together. So we've done some work in all of these different areas. So there's optimization. So fundamentally, why is catastrophic forgetting a problem for neural networks? It's because they are trained using gradient descent, which requires us to learn over, if we want to learn a solution over different types of data, it requires putting that data together and learning from it at the same time. So sampling batches of data, IID, and adjusting the parameters of the network based on those gradients. And so fundamentally, when we unbalance that by seeing only part of the data, seeing only one task of the data or one environmental condition, then we're going to break this. We're going to break this IID assumption, and we're going to and we're going to end up with catastrophic forgetting. We learn one thing, but we forget everything that's been learned before because all of the parameters of the network shift to solve that task that we're looking at. So fundamentally, continual learning comes down to violating our assumptions of IID data, and learning using gradient-based methods. So there's different things that we have come up with as ways to get around this. For instance, so different types of, so EWC, elastic weight consolidation, was an approach that was proposed that modifies adds in a regularization that acts as a proxy. I don't have those previous tasks anymore. I don't have data from them, but I'm going to add in a regularization term that's going to help balance the gradient adaptation. Another family of methods would be around using different architectures. If I use a more modular architecture, then I can sort of protect something that I learned before. I'm not going to be overriding it. So that was the fundamental intuition behind progressive neural networks, and also progress and compress. I'm going to learn from data, then I'm going to keep that in part of my network, and then move on and only touch other parts of the network when I learn new tasks. So there's good solutions there, but you can have problems of scaling. How do I scale this thing if it's going to grow in the space of tasks? And then other types of methods rely on memory and having some notion of, and memory can be as simple as a replay buffer, or can be as complex as the DNC, the differentiable neural computing paper from Alex Graves. And this has a learned read-write memory that's differentiable. This is a much more powerful approach to memory, which can be used to keep old experience, make old experience available. But the training of this can itself suffer from catastrophic forgetting. So pluses and minuses for these different types of approach and different areas in which we might use them. I think that modular approaches can be the simplest and most effective, but they have problems in the lifelong scenario of scaling to a very large number of tasks.
Okay. There was another question that actually specifically mentioned progress and compress. Should the continual learning community work more with the assumption of knowing task boundaries at training time?
Yeah, this is something that we often do, we being researchers in continual learning or multitask learning. We often assume that we've got nice labels for the different tasks, different Atari games, different subsets of an image data set, all sorts of different labels that these are provided. But really, the world is not made up of labeled tasks. I am not doing a task right now. We don't have these hard divisions between the different things that we learn, and so it's very it's a real assumption that we make when we think that we know task boundaries and that we have these hard labeled task boundaries. On the other hand, I understand from personal experience that it's hard to take on all of the different things at once and go directly to the most ambitious, most challenging problem definition for continual learning. So I think that it makes sense to sometimes, assume that there are some labeled tasks, but you should always keep your eyes on the more ambitious case or the more challenging case of not having that, and say to yourself as you're developing a method, will this completely fall down if I lose those task labels? Or task boundaries, or is there a way in which my method is still valuable even in the more challenging setting?
I think you already gave a lot of hints to that third and last question, that section. Given tasks of the same goal but different environment dynamics, what are good approaches to learn an agent that can cover more tasks? Do you want to add something to this, or do you think?
So, I mean, the challenge is in deciding what are the tasks, and in constructing that type of environment. I think that we can either learn from experience of those different environments, or come up with online learning. But sometimes. There needs to be ways in which we can really scale these approaches to go beyond just a few tasks or a few different conditions and really learn on a lot of different things. That then pushes some of the research that needs to be done into the area of designing the problem, designing those task distributions, rather than the agent that learns them. I think that scaling in general is a tricky problem with robotics and continual learning. There aren't a lot of benchmarks out there that are generally accepted. There are not a lot of sort of rigorous benchmarks or data sets that we can use for this.
Okay. So, things doesn't get any simpler, and now we're actually expanding even the range of the questions.
Okay.
Now we're going to reinforcer learning. And one question that was asked was, how do you define the concept of overfitting in RL?
So overfitting is indeed a tricky problem in reinforcement learning, because in a way all of reinforcement learning is overfitting, and that to some extent comes from RL, derives more from the optimization field of computer science rather than from the statistical learning side of computer science. And so the original motivation for RL was much more, I think, driven by, especially in continuous control, was driven by the idea of optimizing the behavior or actions of an agent in a particular environment. There's no notion of wanting to generalize outside of that environment. But when we really bring together deep RL and other areas of machine learning, we start to say, well, wait a minute, where's our test set? How do we evaluate overfitting onto this training domain? And so then the question is, well, what is that task distribution? What is my training set of tasks? What is my test set of tasks? And these distinctions start to feel relatively arbitrary. For instance, in areas like Atari games, then in order to measure overfitting there, we take sampled different starts. So we have humans play the games, and then we sample a different starting location in the game where the agent has to take over control. That is a surprisingly useful way of saying it's the same game, but I want to make sure that I have not overfit to that starting condition. Yes. So that the agent is not just deterministically solving the game, but instead it needs to start in an unknown state and still do well on the game. So there are ways of doing this, but it's always a little bit harder than in a computer vision data set where we can neatly just break it apart into training and test situation. So I think that the overfitting definition is the same for RL as it is for supervised learning, say. It's reducing performance on a held out set because of training as training performance still goes up on the training set. But it's harder to fix it, and it's harder to say, to justify what that set of different tasks is or how we are going to evaluate that overfitting.
There was another question for which I think you started giving hints in your discussion on robotics and continual learning. What is your neural network suggestion or neural network architecture suggestion for dealing with POMDP, partially observed Markov decision process tasks? Could use something different from recurrent neural networks? And I believe you started hinting at this.
It depends on the task. I think that there are three sort of different architectural options that I know of. One is to feed in an observation that spans more time. So you're not just looking at a single observation, but you're stacking together multiple observations. Obviously, that just gives you a discrete, a fixed window of information to do your state estimate from. The other option is the recurrent neural networks, and one can put a transformer type of architecture into this category as well. And then another one might be an actual external, an explicit memory-based model, such as a MemNet or a neural stack or DNC, or these different types of approaches, or episodic memory approaches.
Yes, yeah, we've been working together on navigation, including using the street-learned environment. There was an exciting paper that just came out using episodic memory in the street-learned environment to solve one-shot learning tasks. Okay, so we've been talking a lot about technical content of your research and the fields in which you've been working. And now let's go around organizing and presenting that work. So you are the program co-chair for NeurIPS, which is the world's largest AI conference. You are co-chair along with Marco Aurelio Ramzato, Xuan Tian Lin, and Maria Florina Balkan. And for the first time in its history, and owing to the uncertainties in the pandemic, the conference will be fully online, similarly to iClear, CPR, ACL, ICML, and EML, I guess. We're all online now. So, quick question, which kind of comes back to the earlier one about reading papers. How many submissions to NeurIPS this year?
So we have had a record number of submissions, not too much of a surprise, although we did think that we might get more of a of a hit because of the pandemic, but we extended the deadline. I'm sure that helped. And in the end, we had 9,300 submissions to the conference, which was an increase of about 35% over last year.
So it's still an exponential growth.
We're still exponential.
Great. So coming back to a much earlier question at the beginning of this session, how do you keep up with all that as a researcher?
Oh, it's been a lot of work. I view it's certainly not research; it is service, but I don't begrudge it. It's really exciting to curate this conference. I figure it's a year of work to curate 3 perfect days of content, the best papers, the best talks, the best posters that this community has in 2020. And being able to do that is something that I'm very happy to do. It is a lot of work. I have about 2 days of my week that I just give to NeurIPS to do everything from writing scripts to detect dual submissions or format violations, to answering email questions from authors, reviewers, area chairs, to writing blog posts and updating the website. All sorts of different things that go into being a program chair. It is a lot of work.
So you mentioned curation, and I guess curation is, we can both view it from your perspective, because you're participating in the curating process thanks to this huge community of ACs and reviewers, but also from the perspective of a researcher. Do you think that the only way for a researcher to keep up to date with research is to rely on this curation rather than just have filters on archive?
Good question. Yeah, we put in a lot of work in order to select these papers that we end up accepting, right? Out of those 9,300 submitted papers, we will end up accepting in the end between 20 and 25%. And it's a lot of work that goes into identifying those. And a lot of the ones that we reject will end up on archive. So the question is, what is the value of identifying these? I think that it is important. The whole process of peer review is still very relevant and very important to our field. It's challenging to do at this scale, but we manage to keep on doing it each year. And that process of adding a stamp to papers that get accepted means that they are technically sound, they are relevant to the community, and there's a contribution there. You know, that's the fundamental thing that we look for to accept a paper. And this is still important. This is important for students who are looking to, move on and get their first job after graduation. It's important to professors who are going for tenure. It's important for industrial researchers who want to, convey their results and their ideas to the rest of the community. So I think that we still have a place for it, even though it keeps on scaling, and even though there are other ways to get information from.
How about the issue of, so that's a question that the organizers of EML had, understandably. What are the main challenges in virtual events, like this one you are just attending, and how do you overcome them?
I mean, let's also identify the benefits of being virtual. It is accessible now to the whole world in a way that we have not been able to do through having centralized meetings. So this erases borders and visa problems and all of the rest. So that's really, really valuable. It also means that we now have content. We now have video content. People recording videos for every poster, every paper, means that we've got now this rich, archival content that we didn't have previously, that people are finding really valuable to have access to. The negative side, what I have seen is simply that the community loses. That there's a lot that happens when you're able to walk up to somebody that you don't know and able to say, hi, can I ask you a question? And it's hard to do that in other ways. So I think that just bringing together people out of their regular day-to-day life, bringing them together for a couple of days or a week is really valuable for that cross-pollination of the community for each other. And we have not found a way to replicate that online, although, we've only just started. So we've only been doing this for a few conferences. I'm hopeful that there are ways to have more of a feeling of community and cross-pollination of ideas, even in a virtual forum.
There was some good feedback from iClear, I remember, regarding Rocket Chat and this possibility to approach via chat the presenters. So maybe that at least could reproduce.
I'm also hoping by the time NeurIPS comes around in December, that while it won't be feasible to come together globally into one city, there will be some local meetups, right? That city by city we can start to gather, and that will be safe to do. And I think that can be really nice to have those connections happen, at least on a more local scale.
So it will become a global conference.
Right, exactly.
So you talked about curation. Do you think that the whole system of publishing was going to be changed, or at least affected by those virtual conferences? Are they the future of scientific publishing, or is it just the temporary solution?
What I see as being something that might change is that the conferences are blurring together a little bit, right? The question is, if I've had my paper reviewed for one conference, does it really need to be reviewed if I want to, send it instead to another conference? Where the different main ML conferences, the organizers are all talking together. Increasingly, we're using the same tools. We're using some of the same reviewer pools, et cetera. It feels a little bit like we could be more efficient and a little bit leaner if we started coordinating more. But obviously, there are also problems there with then you get a little bit too pooling too many things the same. It's good to have diversity of different conferences as well. So. But I'm not sure about the future of publishing. There's a lot of discussions there to be had, and a lot of really interesting proposals have been put out over the years. I'm not sure.
Okay. Well, this is very exciting in any way. So I think now we're going to get a bit more personal. Talking about your academic career, which started in the humanities, as I mentioned at the beginning. You studied philosophy and religion at Reed College, which is a liberal arts institution in Portland, Oregon, with a strong reputation for academic rigor. And I just learned via Wikipedia that apparently another famous student at Reed College was Steve Jobs.
That's right.
Yes, and it looks like a very hippie place. So what prompted you to switch to computer science?
I really, let's see here. I actually started a PhD in philosophy after my undergraduate degree. I started a PhD and I went through about a year of it in philosophy. And then I had two realizations. That the world really didn't seem to need more philosophers. At least there weren't a lot of job opportunities for philosophers.
It's a different way of saying it, I guess.
And I also really recognized in myself just the drive to solve problems, to build things, and to be more of a scientist. And so I just started taking computer science classes. My father is a mathematician and used to teach computer science as well. So he sort of prodded me in that direction, and I never really looked back. I was motivated by computer science. I thought that it was a tremendous amount of fun to learn to code. And then when I went to NYU and met Jan LeCun, then I was really taken by the idea of machine learning and robotics. And so those are the two things that sort of drew me in and kept me going. And what I still find motivating. So the second question is going to be, is there value for the philosophy and the religion that I learned early on? Because that's a question that I do often get. I think that really for me, my early years of studying religion and philosophy allowed me to be a good reader, a good writer, and a critical thinker. And I would tend to leave it there. I think that there's a lot of different fields in which go to a good university and learn, and you will learn to think. You will learn to question things. You will learn to, really go deeply into an area. Instead of just learning from a textbook, you will learn how to interrogate an idea and think through something and come up with your own ideas and your own arguments. And that's what being a good scientist is as well. So I have, at that basic level, then I'm very happy with my early career. And yeah.
Well, actually coming back a little bit to NeurIPS, this year, NeurIPS introduced the broader impact statement requirement, which means that every person who submits a paper needs to add this few paragraphs which do not count towards the paper length, with the positive and negative outcomes of their research. And it's essentially an invitation for the authors to exercise critical thinking. Do you think that this kind of approach can help a little bit with ethics in AI?
Yeah, I think that it gets the conversation about ethics and risks, ethical risk. I think it takes that out of sort of the dark corners of AI and brings it into the forefront, saying that as machine learning researchers, AI researchers, we're often not comfortable in talking about negative ethical outcomes, negative outcomes of our research. But I think that it's important that we do have these, think about it and write about it. And that way it becomes something that is there, that's part of the conversation and it's part of the record going forward. I know it's been difficult for authors this year, but this is mainly because it's the first year that we've asked people to do this. I think that as we go forward, this will become something that is more expected and more feels a bit easier. But I think it's important to bring that conversation and bring that critical thinking into what we do with our day-to-day lives. Teach our students that this is part of AI, is thinking about the ethics of our work.
Yeah, that's thank you. I think there is one last question, because we are all here for the pain of it, the pain of research. What are the challenges that you faced in your transition from the humanities to computer science?
I think that there's a quite different style. So learning how to write in a very technical way, rather than writing in the more in a different style as one would do for a philosophy article. It took some time. It took some practice. I think that I certainly had to catch up on a lot of math and coding and things like this. If you don't start to code until you are 20 years old, then it takes a while to catch up on with somebody who's been doing it since they were 10. But all of these things can be learned. I think it's really just about saying, I want to do this, and believing a bit in yourself and getting over those hurdles. I think that other people have other challenges that they deal with as well, even if they've been in more of the science fields, math fields, their whole way through.
Okay. Yes, of course. So we are Exactly on time, with our 10-minute delay. Well, thank you very much. It was really a pleasure, quite exciting, very exciting to talk to you about all those different aspects of your work, of the field, and what led you to it. And I'm just checking here the chat with the organizers, or probably they just see it on the screen.